I want to talk a bit more about the form of the solution that we derived last time for the tank filling problem. Alright, so the solution that we derived is the following. So the solution consists of two parts. This first exponentially decaying term that propagates the influence of the initial condition on the final solution. And you can see that what the initial water level in the tank is decays exponentially with time, and the time scale for this decay is tau. And so if tau is a very small number, then the exponent in the exponential term is going to have a very large magnitude. With the minus sign will make it decay very quickly. And so the influence of the initial condition will decay away rapidly if tau is small. On the other hand, if tau is a very big number, then the exponent, its magnitude, will be very small and the decay will be much slower. And so the system will remember its initial condition for a longer amount of time, for a longer time scale. So you could think of tau sort of the time scale for the memory of the system to its initial condition. The same time scale appears here in this exponential term inside the integral for propagating the input of water into the tank. You notice that this term here looks very similar to this one. The dimensions of r primed are at t prime dt primed. The dimension of this is a volume, is length cubed. And so when we divide by a, if I divide by a, then this becomes just a length. So it's a height. So this term here gives you height. The exponential is not non-dimensional. And so you can see that this little bit here is like an input of height if I add the a to the water level. And then it decays exponentially with the same kind of time scale as the initial condition. So here we can think of this as a little height increment. If I put the a in here, that happened at time t prime, and then from time t prime onwards it starts decay with the same time scale tau. So the solution, we can view it as having two times t, and then there's a time t prime for when we add the increments of water from the inflow. And so I'm going to write, I want to try to explain what this looks like. So a little bit unconventionally, I'm going to make the time axis t point downwards, and then I'm going to make the t prime axis move along this direction. This is time t naught, and this is also time t naught in this axis. And then along the main diagonal, this is the line t equal to t primed. So in this domain, we have t prime greater than t, and in this domain we have t greater than t prime. So out here, this would correspond to sources that happen in the future, and so clearly these cannot influence the solution at time t. So out here, there's nothing going on out here. The inputs happen along this line, along this diagonal line, and then their influence propagates forward in time. So the initial height, h naught, that we have at h naught, its evolution as time progresses decays exponentially along this axis. So if I was to plot the influence of h naught along the time axis, what I would find is something like this. So this is h naught times the exponential term. Let me turn it over so I can write exponential of t minus t prime, t minus t naught over tau with a minus. you can't really see, but this is meant to be this term, and so it will decay like this. And the time scale for decay is tau. So this term, and it decays. And then what we have over here is a superposition, or the addition of new height increments that come from the integrand multiplied by a. So at a later time t primed, we have an increment again, maybe it's a big one, and then it starts decaying exponentially. And then at a later time we have another input, and it decays. And depending on what the time history of r prime, we could think of having a continuum of these impulses coming in at different, this is a different t primed. So this one is at t primed is 0, that's the initial condition. Then at t prime is t naught. Then a little bit beyond t naught we have a new input from r, and then it decays. Then a new input from r prime at a later time, and it decays. And in reality we have a continuum of inputs from r primed. And so if I pick a particular time t at which I want to evaluate h of t, I have to sum up the contributions along this line over here, that's the integral, from t naught over here all the way out to here, which is t. So I'm going to sum, and what I'm summing are terms that came in at different times. So there's going to be one input over here, this t prime, and it will decay exponentially for this time interval. This is t prime minus t. And then some later time there'll be another input, and it decays. It came in at a later t primed, right? So there's successive t primes, the inputs come in, and then they decay. So the more recent ones have decayed much less, because for a shorter period of time, because they've been input more recently, closer to time t when we evaluate the solution. They will continue decaying into the future, but at this point they've decayed only a little bit. And the further back in time we go, further away from t, then the influence of the input has decayed more and more. So, and eventually we forget the total influence of sources of water into the tank if they're sufficiently far back in time. Okay, I don't know if this little diagram was useful. I want to show an analogous diagram for the discrete solution that we obtain from using the Euler-Ford time-stepping scheme. And I want to show you that is a very similar form to this expression. Alright, so the Euler-Ford scheme is the following. Alright, so I'm going to use a little square bracket with the ends to point out that these h and r in the Euler-Ford are now discretized and defined only at integer values of inputs. And so if I rearrange this expression a little bit, I get the following. So I've collected the terms so that I have h of n plus 1 on its own on this side, and then on the right hand side I have the contribution from hn over here, which multiplies 1, and then the contribution from this with a minus delta t over tau times hn, and then I have the delta t over a times r of n. And I'm going to further simplify the notation one more time so that it's easier to write the final solution on the paper. Oops, hn. So I introduce a factor a here, and then over here I'll just call this one x n. So what's a? So a is defined to be 1 minus delta t over tau. So that's just a scalar, a number. And x of n is equal to delta t over a r of n. So this, the dimensions of this is a height. It's a height increment that happens over the time interval delta t, right? R is a volume per unit time. If I multiply by delta t, it's now a volume. If I divide by the area, it's now a height. So this is a little height increment to h that comes from the source term at the discrete time n. And then we have the initial condition, h of 0, right? So h of 0, which is equal to h naught, is given. And from there, we can now use the Euler forward scheme to calculate h1. Oh, here I need a 1. So h1 is going to be this factor a multiplying h0 plus x0. Then h2 is going to be a times h1, which is this expression. So now we'll have an a squared h of 0 plus a x of 0 plus x of 1. And then h3 will be a times h2, which is this expression. So we'll get a cubed h of 0 plus a squared x of 0, yes, plus a x of 1 plus x of 2. Then h4, and hopefully you're starting to see the pattern. And so on. And you can now see that you have the solution as time evolves. So out here I have time increasing, and along this axis I'm the solution at some time, discrete time 7 here, at the 7 time step, is the contribution of different terms. One from the initial condition, one from the initial source at time 0, one from the source at time 1, one from the source at time 2, time 3, times 4, times 5, times 6. And the sources at time 7 have not come in yet, so they don't influence the solution yet. And so along this axis, out here, this is the analog of t primed. And so there's t naught comes in here, then t1, or t0, t1, these two come in at t0, t1, t2, and so on. And so you get this kind of triangle shape, and then the influence of all the initial conditions, they start at successively later times, and then they decay exponentially. So how decayed they are depends on how many time steps I've taken. So for these to be decaying, it's important that a, the magnitude of a, has to be less than 1. If the magnitude of a is greater than 1, then these will blow up. Right? They're going to grow exponentially because we're raising it to higher and higher powers. And so if I go back at the definition of a, if I want this to be less than 1, then a sufficient condition for this to be is that delta t over tau must be less than 1. Remember, delta t is positive and tau is positive, so I want delta t to be less than tau. Where tau is the kind of intrinsic time scale of the system, I need to take my time step to be smaller than that time scale. So in other words, I have to be able to resolve this decaying exponential. If my time step is too big and I step over the kind of characteristic decay time scale, then the Euler forward solution blows up, and it's not faithful to the continuous system that I'm trying to solve. All right, we can try this on the computer, and I could show you how the code will blow up in situation where I pick my delta t to be too big. All right, so over here on the right, I have my text editor with my MATLAB script that will simulate the tank, the leaky tank problem for the case of a sinusoidal input function. So the flow in follows a sine function with a period given by t, capital T here, which is a parameter which I can set. In the first example, I set it down here to be 2 minutes, or 120 seconds. And I'm going to simulate it using the Euler forward time stepping scheme as I've done over here. So I'm going to follow this scheme. So if we go through the code briefly, A is the cross-sectional area of the tank, which is just 1 square meter. Tau, the intrinsic time scale for the drain, which is 2 minutes. I picked it for this particular example. And I also picked the period to be 2 minutes, 120 seconds. This is the amplitude of the sinusoidal forcing. It's 1,000th of a cubic meter per second. And this is the flow function. And it oscillates sinusoidally from 0 to 1 with a period to t, capital T, which in this case is set to 2 minutes. And then for time stepping, let's pick a time step of 10 seconds. So that'll be 12 time steps per period, or 12 time steps per intrinsic timescale tau. And then I have the discrete time for 15 minutes, the forcing function x, like I have over here, right? dt times r divided by a. Then I have the discrete height, where it's discretized in time. And the initial condition, I put in 1/4 of a meter. And then I define the parameter a, that appears over here. 1 minus the ratio of delta t to tau. And then I do the loop to do the Euler forward time stepping scheme. So h at times k is a times h at the previous time step plus the input from the source function. And then I make some plots. I plot the water level in the tank in blue and the forcing x. Sorry, the water level in blue and the forcing in red. And label the axes. So let's run it and see what we get. And so you can see the solution. At first, the water level is 1/4 meter, and it drops, and then eventually it settles in on some steady state condition, oscillating between 0.1 and 0.15 meters height. And the input function oscillates over here between 0 and 0.001, I guess 0.002, right? The amplitude of the sine is between -1 and 1. And when I multiply by 0.001, I get an amplitude of 0.001. So it'll oscillate from a maximum of 0.002 to a minimum of 0. All right, let's look at what happens. This is a discretized solution. If we want to go to the continuous one, we should make delta t smaller. So let me reduce delta t and run the model again. And the solution looks roughly the same, right? A little bit offset. Now the x function looks like it changes a lot, and that's because x is the amount of water input per delta t. So when I reduce delta t, x decreases, right? So that's a little bit counterintuitive because x is inherently discrete. So the meaning of x is not really the rate. It's not a rate coefficient. So maybe I should, to make it clearer, I'm not going to plot both on the same graph. I'll plot figure 1. Then I'll have something that doesn't depend on my time step size. So it'll be the actual rate of input. Remember, when I redefined x, I multiplied through by dt. So x is the amount of water input in one time step. So when I change the time step, x decreases. Now the rate, on the other hand, doesn't change. So what I'm going to plot is r over a. So I get a proper rate independent of the discretization. All right, so that's figure 1. And in figure 2, the solution, time. All right, let's try it again. CLF, dx4. Okay, so this is the input function bouncing around between 0 and 2 times 10 to the minus 3. And this is the response starting at 1/4 meter and then decaying with a time scale of roughly 2 minutes, and then eventually settling on the periodic final state. And if I make delta t bigger, but still well within the criteria that we established down here for the stability. I should still have a stable solution, slightly less accurate, but still acceptable. Oh, I forgot to do hold on this one. Hold on. I'll do that so that I can plot the solutions for different time steps on the same graph. Alright, so that's the solution using a time step of 10 seconds. Then I'll make the more accurate one with a time step of 1 second. So now there's slightly different the minimums, but eventually it seems to settle into roughly the same solution. And now let's do it again, but now make the time step bigger. So I had 10. Now I'm going to make it to be 120 seconds. So that is not very good in that A here will be 0, right? So if I have delta t over tau is going to be exactly equal to 1 and A will be 0. So although the solution will not blow up, there will be no propagation of the solution at different times. And so we'll get a completely spurious solution. Let's try it. Right, so the water level drops and it just follows kind of a steady state. And here the input is, I only sample every 2 minutes, so my time steps, so it always gets the forcing to be exactly equal to 1 times 10 to the minus 3, right? So I miss the full oscillation down to the lows and the high. That is called aliasing, where your time step is too big and you don't resolve the frequency or the period of the forcing or the solution. And then the solution doesn't see any of the oscillation. So let's go the other direction where I'm now bigger. I'm going to pick it to be 240 seconds. So now delta t over tau is going to be equal to 2. So 1 minus 2 is minus 1. So A here will just be on the edge of stability, so it will not grow exponentially, but it will oscillate. It'll change signs, right, from negative, positive, negative, depending on whether it's an odd time step or an even time step. So we should see a spurious oscillation this time. Let's try it. And now we're starting to see this kind of weird oscillation. I don't have enough time steps to really see what happens, so let me run it longer. Where's my time? So instead of running for 15 minutes, let's run it for 60 minutes. And then you can see this spurious oscillation at every time step. And right, again, since I'm taking a step every every 4 minutes, and the period of the oscillation is only 2 minutes, I'm again aliasing the frequency of the forcing, and it just looks like a steady forcing. All right, now let's go crazy and make this even bigger. So I'll just make it, I'll double it again. So 240, that'll be 480. And now if I have 480, this will be 4, right? Yes. Delta t over tau will be 4. 1 minus 4 is minus 3. So it will not only oscillate because it has a negative sign, so it'll go positive, negative, but since the magnitude of A is bigger than 1, it'll blow up exponentially. So now since I have a bigger time step, let me run it longer for 600 minutes. And now you can see here the forcing is aliased, but the solution is growing. It looks like nothing's changing, but that's just because the scale here is already up to 10 to the power 34. So it's just growing exponentially very quickly. So this is kind of showing the stability properties of the Euler-Lefort scheme. You have to pick the time step smaller than the characteristic time scale of the system. And in this case, I picked tau to be 120 seconds, so my delta t has to be less than that. So let's go back to a reasonable time step of 10 seconds. Clear all CLF. Close all. And this is the solution. This is the forcing. I guess I'm running so long you can't see anything. Let me run it for a shorter period of time. 20 minutes. Oops. CLF, close all. Next 4. And that looks more reasonable.